All right, welcome everyone. We haven't had class in a week and a half, and so we're gonna make a video real quick. And it's not gonna be real quick because there's so much to say. Let's go. I have this super janky setup um, at home, and yeah, we're gonna make it work. And this is so awkward because I don't even know some of you. We haven't had class yet. And I'm making this for Dr. Castro's classes also. So you might not know him either. And, you're going to watch this video tomorrow, Monday, on the snow day. And, all right, what are we doing? Let's begin. Um, Here's my question for you, and you might know something already about this topic, but you might not. So let's just jump right in. What is calculus? This is the lecture I would have given on the very first day of the semester, which was supposed to be last week. So what is calculus? What's going on? What are we doing this whole semester? And in fact, this is a year-long course, so we're going to start this semester and finish next semester? Okay, calculus is and I'm gonna write this down. Oh man. Okay. The analysis of infinitely infinitely small and infinitely large quantities. And infinitely large quantities. Okay, so if you have some infinitely small quantities that you want to manage, or some infinitely large quantities that you want to manage, or perhaps managing them together, then you need some calculus. So, all right, that's kind of like one answer. Let's give another answer that's basically the same thing. It's sort of a collection of advanced techniques, a collection of advanced techniques for manipulating these quantities. So this is maybe repetitive or something, manipulating these quantities. Okay, so things can go wrong when you are manipulating, infinitely large and infinitely small quantities. So you need some techniques. So we are going to discover some techniques and sort of show that it works. And the reason why it's called calculus, it's really sort of a shorthand for the calculus of infinitesimals, the calculus of infinitesimals. And what are infinitesimals? Okay, it's kind of controversial. They are these infinitely small quantities, and calculus is kind of just an old sort of Latin word for, method of calculating. So if you really want to know what calculus is, it is a method for calculating with infinitely small things. Okay, and the thing that makes this class really so different from pre-calculus, well, there's a lot of things that make it different from pre-calculus. Although we've sort of made the pre-calculus class at Blair pretty good, so maybe there you won't sense a gigantic difference. But in pre-calculus, in some sense, we were just kind of doing a survey of many different topics. We do a little bit of this, a little bit of that. Calculus is going to be more focused, so we are going to begin very slowly and build and build and build like a body of understanding. And so we're going to have sort of like you might expect in a geometry class. And I know that your geometry class that you took in middle school might not actually have this property, but what's supposed to happen in a geometry class is, at the very beginning, you encounter certain sort of shapes and objects. Oh, point, line, segment, ray, triangle, and angle, and so then slowly you build precise definitions for these objects that you're supposed to learn and understand, and we can define more complicated objects from these simpler objects. And then, you conjecture certain relationships. Oh, I believe that this is true, SAS is something like that. And then you have certain, postulates, certain things that are too simple to prove that we just assume are true. And from that, we build up and we prove, more and more complicated theorems. And so, early on in the year, you prove the isosceles triangle theorem, and then you use that over and over again. And so the point is, in a geometry class, you are expected to um, know lots of definitions of lots of things. You are expected to prove lots of, come on, man. You're expected to prove lots of, what is going on? Okay. Um, Something bad is happening with my, okay. You're, what? I'm being told that I have to, what's going on? No, 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 no. What? Can I literally not continue using this thing? Okay. Sorry. I apologize for all of this business. I'm gonna hope that doesn't happen again, but it might. Okay, so yeah, like I was saying, in a kind of a geometry class, you are expected. Oh man, I have to do this all over again too. You are expected to learn these theorems, to remember them, and to apply them over and over again, and they become kind of part of your knowledge, and your knowledge sort of builds, slowly throughout the year as you encounter more and more of these theorems. So, okay, calculus is going to be like that. In other words, it's a sort of a highly structured class. We're going in a certain kind of order, and we're going to continue using all the things that we learned from the very beginning of the year. All right, that was like too long. Let's jump into to what is calculus kind of like? What's it all about? Let's understand, like, before we try to solve problems, what even are the problems? Okay, well, you can answer this question, and our book kind of does this in the very first section of chapter 2, which you can take a look at. That there are two problems of calculus. So the first problem of calculus is the area problem. Okay, what is the area problem? Well, the area problem is basically the problem of finding the areas of things. And okay, how do you find the area of stuff? Okay, well, I will now condense in like 10 short minutes every single thing that you learned when you were maybe more when you were learning geometry in middle school. How do we find the areas of things? Well, an extremely intellectual approach is to sort of do it axiomatically, to say, okay, what does area even mean? Well, area is kind of like the space that something takes up, and you measure that in sort of square units. Okay, and somehow it's like an axiom or something that the area of a square of side length 1, this is like the simplest possible object, is 1. It's 1 square unit. Okay, so that's pretty exciting. Great. We now know. So what I would like you to do is to enter this kind of thought experiment with me, where you pretend to not know anything about area whatsoever. So take every single formula that you ever learned in middle school or earlier, and kind of delete it from your mind, and consider the problem anew. So what do we know? We know the area of a square of side length 1 is 1. Okay, well, what's another kind of more complicated object? Well, how about a square which does not have side length 1, but which has side length like, 3 or something like that. So if this is 3 and this is 3, well, how are we going to find the area of a square of side length 3? Well, I think it's pretty obvious that in this case we have an option. The option is to split this this segment of length 3 up into 3 pieces. And so then we kind of can get like this sort of thing going on, where these are all, 1. And so what we actually have here are 9 squares. And of course, what are the areas of all of these squares? They all each have 1. And so therefore, we see that the area of this whole square is 9. Aries 9. Okay, duh. This really is kind of like second grade stuff, or maybe third grade stuff. Obviously, the area of a square of side length 3 is 9, but okay, we just proved it. We by decomposing it into a whole bunch of unit squares. Okay, let's do something. So now we have kind of, you might say, a square theorem. The square theorem says that the area of a square of side length n is just n squared, and that's why we call it n squared, in case no one has ever mentioned this to you. Um, of course, that argument only applies if n is a whole number. So what if n is something more complicated? So what if you have a square of side length, 1/3? All right, so this is a little bit cute. If this is 1/3 and this is 1/3, this is kind of a strange question. How can we compute the area of this square, based on things we know already? Well, if fundamentally the only thing we know is the area of a square of side length 1, then what we can do is we can just kind of extend this out until it's 1. It's kind of like a brilliant idea. Picture not to scale. Hold on. Let's fix this a little bit. Hmm. Um, yeah. And now what we see here is a bigger picture. Man, that looks terrible. Consisting of um, a whole bunch of squares. How many squares do we have? Well, what are the areas of these squares? Well, we don't know. We're pretending that we don't know what the area of this square is. Let's just call it x. But as the side length of this big square has now been made 1, what I can tell you is that this overall square, by our sort of basic axiom for squares, has area 1. And so therefore the area of this square, it sort of like takes, 9 of these x's together, gives you a square of sine length 1. And so x is 1/9. Okay, so now I know how to find the area of squares of whose side lengths are integers. I also know how to find the areas of squares whose side lengths are unit fractions. Okay, come on. What are we doing here? Well, going through all the different kinds of numbers? Yeah, that's exactly what we're doing. Well, let's do something. Let's do something kind of similar. Maybe for what about if this? No. What about if the side of the square is like? Oh my God. If the side of the square is like 7/2, then what? Okay, so I think if we were all alive, I think you would all be telling me what I can do here. This is kind of a more complicated fraction, but all right, same sort of strategy, right? Double the side lengths to create a new situation in which here now we have a square of side length 7, and then you can apply the kind of square theorem for integers. And once again, okay, let's use a different variable. Let's call this like z or something. So if these are all z's, then what have I just learned? I've just learned that if you give me 4 of these z's, then I get added together, give me a square of side length, give me a square with area 49 by the square theorem, and so z is 49 over 4. All right, so this is kind of a very sort of intellectual approach that takes very seriously, these distinctions between, whole numbers and unit fractions and more complicated rational numbers. But I think now you should be convinced of the square theorem, but you should also maybe be a little bit worried because if you think, okay, Mr. Rose, you've set a really high bar here. You're asking me to like, prove in a very careful sense, these theorems. Yeah, I am. And suddenly you might be worried, okay, well, what about these other kinds of numbers that are out there, like, square root of 5, for example? What should be the area of a square whose side length is square root of 5? Well, we kind of want the answer to be that the area of the square is 5, but this is sort of revealing that we don't really understand perhaps irrational numbers in the same deep way that we do rational numbers. And so this is kind of a more advanced question, and it's kind of a deep question and a tricky question. So we won't talk about that now. All right, let's keep going. So far, what have we done? Squares. So that's like pretty embarrassing that we've only made it that far. What other kinds of shapes are there? In class, I would ask you guys, what are the next most complicated shapes? Well, rectangles. And all right, one approach to take with rectangles is to sort of do it all over again, everything that we've just done. And suppose you have a rectangle of side length 3 and side length 5. Well, this can also be split up into unit squares. And so we could just do that and we could sort of see, okay, clearly the answer is 15. You get sort of like a rectangle theorem. But then you would have to deal with all of these, special cases about whether A and B are maybe one of them is a whole number, one of them is a fraction, and that would be kind of annoying. So instead, maybe we could do something, more intellectual. So sort of new idea. Can I build on all of that casework I did on the previous slide and somehow prove a theorem for rectangles that in terms of the theorem for squares? And the answer is yes. And this is, again, something that, you could do this in a middle school class, but probably you did not do anything, quite this intellectual. So, okay, now what I ask you is consider a rectangle with side length A and B, where now I don't presuppose any facts about A and B, like what kind of number they are. Can you sort of prove to me what the area of this rectangle is? And the answer is, yeah, we can do this, and it's very interesting. What we can do is we can turn it into a square. And we can do this by extending this side by A and extending this side by B. And suddenly, what's happening before me is a square. It's a bad picture. Okay, and yeah, what what can be said about this square? Well, there's kind of like this piece, there's this piece, and okay, this is too terrible to be. Let me fix this. Yeah, good. All right, so what do we have here? Well, by sort of decomposition, what we have is whatever this rectangle is, which I'm pretending I don't know what this rectangle is. So to be consistent, I will call this X, and X is the goal, right? But here I have another rectangle whose side length is also A times B. So this is kind of like another X. But this is, by my square theorem, A squared, and this is, by my squared theorem, B squared. Okay, and yet the entire thing is also a square and of side length A plus B. Okay, so using only facts that have already sort of proven about squares, I can now tell you that A plus B quantity squared, that's the area of the entire square, is A squared plus B squared plus 2x. And now I'll sort of lean on some, algebra facts or something. And oh, okay, I think you see where this is going. This is 2ab plus b squared. And so here I am. I have plus 2x. I have now proven to you, do a little bit of algebra, that x is ab. Okay, so this is how you would sort of prove the rectangle formula, from the square formula, something like that. Okay, getting a little bit out of control, perhaps. But all right, let's just push on. What's the next most complicated um, object that you might want to find the area of after you've dealt with squares and rectangles? Yeah, that's right. Triangles. And there's a particular kind of triangle that you especially want to find the area of. That is right triangles. Okay. So here's a right triangle with side length A and B. What is the area of this square? Well, we can just perform a kind of a similar analysis, right? If you every right triangle kind of wants to be a rectangle, and if you just pretend temporarily that you don't know what this is, well, we've just built a second copy of it over here, and now we see, oh my God, now we see that, what do we see? That two of these x's is a times b, and therefore x is ab over 2. So this is sort of a proof of the formula for the area of a right triangle. Okay, that's kind of like cute or something. What can we do, better? Or this is just very specific to right triangles. What about kind of like a general triangle? Okay, and you'd be surprised how badly this is sort of taught in, fifth grade, seventh grade, ninth grade, whatever. Here is a triangle, and, rumor has it that the triangle formula is in terms of the base, which can be any one of the sides, and the height, so the altitude to that base. Okay, and what's the deal here? Well, all right. What are we gonna do? We're gonna do it. And here, how this problem kind of wants to be solved. Let's get some new colors involved. Is by decomposing it. Every one of these objects can be sort of turned into kind of like a rectangle in a kind of way. So, put it in a box is kind of the strategy to finding the area of anything. And so here, what we can do is we can enclose this entire non-right triangle in a box, a rectangle. And now we can see, so this is H, this is also H, this is also B. And and now, looking at these two right triangles, we can see that they each have the same area. And looking at these two right triangles, we can see that they also have the same area because they're congruent to each other. And therefore, to complete the analysis, we can just say, okay, our triangle takes up precisely half of this box. And therefore, the area of our triangle has to be half of base times height because it fills up half of that rectangle. Okay, Man, what are we doing? We're just finding the areas of shapes. Mr. Rose, it seems like a review of middle school geometry. Yeah, it is. All this stuff's kind of important to know. Should we do one that's even harder? Let's do parallelograms. Okay, I'm gonna give you sort of a less good proof, and then I'm gonna give you a good proof for the area of a parallelogram. All right. Well, one way, the way that they often teach you this in middle school or something is if you have a parallelogram. So it looks, kind of like this, and this is the base, and this is the height. Then, so they say, you can just turn it into a rectangle in a certain kind of way by taking this rectangle over here and sort of, moving it over here. And it becomes clear from this that the new shape that you get. What have I just done here? Hmm. Sorry. Let me go back a couple steps. That's not what I meant to do. I meant to cut off one of those triangles. Let's do that. Hmm. So actually, okay. Let's put that back again. That's the height. Sorry, I lost my train of thought. That's the height. And here, what we're now going to do is take this triangle and sort of move it over here into this spot. And this gives me a new triangle. Oh man. Excuse me, a new rectangle rather. And the area of this rectangle is base times height. So therefore, the area of this parallelogram is the same. Okay, that's fine in a kind of a way. That was a terrible picture. What's a maybe a better way, or what's wrong with this? Well, what's wrong with this is that this cut off a triangle and stick it over to the other side argument works for some parallelograms, but not others. For example, if you have a very kind of skinny parallelogram like this, then you would also like the theorem to be true. It is true that if this is the base and this is the height, you would also like it to be true that the area of this parallelogram is base times height. However, this argument cannot be this argument from the this proof that we have above. This argument cannot be applied to this particular parallelogram. Not in this way. You could cut off kind of a different triangle. Over here, you could cut off a triangle. But here specifically, I want the formula to be true for this base and this height. And for this base and this height, I cannot cut off a piece and stick it over here. This actually reveals that our proof from the previous page was also a little bit incomplete. Because over here, notice that when I picked this triangle, I picked a very cooperative one. But if I were to have picked some sort of obtuse triangle, then it would be kind of a more complicated argument. And so actually, what some people do is they'll prove the formula for parallelograms. And if you have proven it for every parallelogram, then every triangle is just half a parallelogram. And you can kind of do it that way. All right, so what's a better argument? It's kind of subtle. Okay, is this a good use of our time? I don't know, but I'm making a video. So, all right, it looks like this. Let me begin. So I'm gonna try to redraw this. So here's our, hold on, not weird enough. So, shoom, shoom, shoom. Okay, so this is my base, and this is also base, and um, this is my height. Okay, so what is the area of this parallelogram and why? Okay, well, let's pretend that we don't know. So we're going to give it a name. We're going to call this parallelogram X. Or we're going to call the area of this parallelogram X. Okay. Yeah, and we're now going to pursue the method called put it in a box. Okay, so to put it in a box, I'm now going to extend this whole thing out and down here. Okay. So yeah. Great. What do I know now? What do I know now? Well, I don't know anything except what I can tell you is that I have two equal shapes here. So I don't know what their areas are, but I'm just going to call this Y, and I'm going to call this um, Y also. Am I doing this right? Sure am. Yeah. Okay. And so somehow, like the area of the entire parallelogram is, x plus 2y or something like that. Um, yeah. But also, I have a wait, completely lost my train of thought. Um, oh my God. Why is this happening? Wow. It's kind of ruining my video. No, I don't want to upgrade to premium. And I would like you to stop telling me to do that. Blank. Yeah. Okay, wow. I guess it's just gonna keep doing that every 10 minutes. Good. Wait a second. Oh man. What the heck happened? Yeah. Um, whoa. Okay. Whoa. All right, very professional video we have here. Okay, so that's just gonna keep happening every 10 minutes. Okay, so what are we doing? We've sort of decomposed this big rectangle into three pieces: a Y, and an X. But then also, there is a different way in which we can decompose the figure. We can also decompose it into kind of confused by my own world here, but I think I know what I'm doing. Okay, so I'm now going to draw this little orange rectangle. And what can I say about this little orange rectangle? Well, it is, of course, base times height by the, um, uh, yeah, by the rectangle theorem. I need to pause to think for a second. And so what the heck am I trying to say? That's base times height. The whole thing is two. Oh, no, so the area of the whole thing is 2x plus y. Um, but then also, oh, okay. So, but then also, the two y's can be kind of smushed together to make a big rectangle. Okay, I'm not explaining this super well, but basically what it comes down to is um, that x has to be base times height. I'm just going to say this in words instead of trying to write everything down. X has to be base times height because on the one hand, um, the two y's pushed together make make this okay. Yeah. 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 So it's kind of like this. It's kind of like this. I should have thought of this a little bit before. I think I also got stuck trying to do this last year, and we're getting sort of off topic, but this whole rectangle can be kind of decomposed in two ways. It can be decomposed into a sort of green rectangle and a orange rectangle, but it can also be decomposed into the two Y triangles and the X weird parallelogram. But of course, what is the area of this big green rectangle? Its area is 2y because this right triangle is clearly like half of it. And so on the one hand, 2x, okay, so we made it this far. On the one hand, 2 y plus x gives you the area of the entire big rectangle. But on the other hand, it's also true that 2y, that is the area of the green, plus base times height gives you the area of the entire rectangle. And so x is base times height. Okay, this is kind of interest, maybe only to sort of like a few people. And so this is the way you prove the formula for the area of a parallelogram. All right, I hope you like skip through this part. Let's kind of keep it moving. What's left? We're pretty much done. What's left? Maybe trapezoids. And how do you find the area of trapezoids? Well, you can do something like this, maybe, and then let's call this like base one, call this base two, call this like, h for height or something. And I would like to find the area of this trapezoid. Well, one way to do this is once again to pretend that you don't know the area of this trapezoid and double it. So just make a new one, and this new trapezoid will be over here, and it will be something like this. So this is base one, and this is base two. Well, now we have, since these are parallel, that's built into the definition of trapezoid, and now the opposite sides are also equal because you made it that way. Now we have a parallelogram, and since the two trapezoids are both equal, then that what we learn is that twice the area of this trapezoid is going to be the area of this big parallelogram, which is b1 plus b2 times h. So this is the formula for the area of a parallelogram. It's kind of like, the average of the bases times the height, people say, but maybe that's best understood as two of the same trapezoid back to back, give you a big parallelogram. Okay, where are we going with all this? We've basically just redoing, middle school math or something like that, so far. Okay, and there's maybe like kind of one step left or something, which is, well, that's probably good enough. If you give me any shape, now that I know how to find the area of a parallelogram, now that a triangle is half of a parallelogram, now basically any shape which is made up of triangles, I can find the area of. And so if you give me something sort of more complicated, like a pentagon or something like that, and you ask me to find the area of this pentagon, well, if you give me sufficient information such that I can sort of decompose this pentagon into a whole bunch of smaller shapes. And if you give me sufficient information about this pentagon, which determines the pentagon, like for example, all the sides and all the angles, I can go on a kind of a law of cosines, hunt piece by piece through these various triangles and calculate the areas of all of them individually, and therefore find the area of the entire shape. All right, I would like to declare us now experts and to declare us, done or something with finding the areas of all these kinds of basic shapes from middle school. Mm, but one so-called basic shape is missing. What is the first shape for which it is like really hard to find the area? This was all kind of like easy stuff. Although we took a particularly sort of theoretical, intellectual approach to that. What's the hard stuff? Yeah, that's right, circles. How do you find the area of a circle is actually just a really hard question. Circles are curvy, and that makes them pretty difficult. How am I going to find the area of this circle? Well, maybe someone told you this in third grade. Maybe you've never learned this before. Our old methods are not going to work, and our old methods were basically split it up into a bunch of triangles, or maybe put it in a box. But here, that's not going to work. We have sort of curviness, and curviness is kind of difficult. So, okay, well, one thing we could try to do is we could try to split it up into, well, I wouldn't call them triangles because they're not triangles, they're sectors. If I could find the area of one of these sectors, then I could just multiply by the number of them. But of course, I can't find the area of these sectors because that's just as difficult as the original problem of trying to find the area of the circle. So what can I do? Well, you can rearrange these sectors in a certain kind of way. And if you do this, okay, um, eager to get back to school where my penmanship is better. But if you arrange the eight sectors, in this case it's eight, of this circle in a certain way, if this circle had radius r, then I hope everyone sees that what we get is a kind of a parallelogram type shape. In fact, if you really squint, you can basically call it like a rectangle. And what can I say about this rectangle? Well, roughly speaking, the height of this rectangle is the radius of the circle. And roughly speaking, the um, length of this rectangle is this plus this plus this plus this. So that's half of the circumference, half the circumference. And so if you really kind of squint and then what you can sort of tell yourself is that the area of any the area of any sorry the area of any circle is the area of any circle is just going to be the same as the area of this rectangle that you get by smushing all the sectors together. And so it's going to be 1 half c times r. And this is sort of the cool kids way of saying the formula for the area of the circle because it sort of invokes the actual reasoning behind it. It's just half the circumference times the radius. Okay, and of course, if you write this in a more sort of traditional way, the circumference of any circle is 2 pi r. That's kind of just what pi is. It's the ratio between the circumference and the diameter, and times r. And so the 1 half and the 2 cancel, and you get this pi r squared formula for middle school. Okay, so that's pretty exciting. So what did we do? If we were here live in school, some people would say, but wait, that's a lie because this is not actually a rectangle. It's actually like some curvy, bumpy thing that kind of looks like a parallelogram, so this formula is like invalid or something like that. I agree. But I can try to make it better by splitting this up not into eight sectors, but into 16 sectors. And if you split these up into 16 sectors, you'll get something that looks a lot more like a rectangle. And if you go 32 or something like that, you'll get something which is maybe almost indistinguishable to the naked eye from a true rectangle. And the more and more pieces you slice this circle up into, then these curvy bits become flatter and flatter, and these sectors look more and more like real triangles, and so you sort of converge on the rectangle shape. And so, if you want to prove the area of a circle in the way that we just did, you really need to kind of do sort of this infinite process. And so, okay, why are we talking about all this? All this was kind of like a big build-up to the first hard problem, which is trying to find the area of a circle. And trying to find the area of a circle really does require you to do what I call baby calculus. And baby calculus is when you have some kind of well, it's basically like doing casual kind of calculus. In this case, the casual calculus that we have to do is split the circle up into an infinite number of these sectors and then kind of put them all back together again into a rectangle. And so what we're really doing is we're adding up an infinite number of infinitely small things. And that is something that's kind of hard and requires, some care. Okay, so this is all very sort of interesting for like historical reasons. I don't know, usually teenagers don't care about, history and stuff, but the first person to really do this that we have records of was Archimedes. This is about 300 AD, and he found the area of a circle in this exact way. And he had this technique called, the method of exhaustion. And the method of exhaustion said that to find the area of some kind of curved region, you would exhaust it with known shapes. And okay, so he actually took a circle and he sort of inscribed inside this circle a sequence of regular polygons. And so if you take, for example, a regular hexagon, you can fit a regular hexagon inside of this circle. And we can calculate the area of a regular hexagon exactly. And so clearly the area of a circle is going to be, a little bit more. But if you then turn around and circumscribe about, hope make sure I'm doing this right. Yeah. So let's connect some dots first to make it look pretty. Um, okay, yeah, that's not exactly what I wanted to do, but sure. I guess this works something like this. Hmm. Hmm. Oops. Okay, good enough. What we have here, whoa, is a circumscribed hexagon. So an inscribed hexagon is the hexagon drawn inside the circle. A circumscribed hexagon is the hexagon drawn around the circle. And so clearly the total area of the circle is going to be somewhere in between those two. And so that gives you a pretty good estimate. Actually, you can already kind of get a good estimate for the area of a circle just with hexagons. If you go up to, say, dodecagons, 12 gons, you're already getting like a quite good estimate. I think the area of the internal dodecagon is 3, so that's pretty close to pi. What Archimedes actually did is he did it with a 96 gon. And okay, this is obviously he had no calculators to do all his computations by hand. He had to do hand, some kind of trig identities or something like that, half angle formulas all by hand, all the radicals all by hand. And mhm, he got a formula for the area of a circle that was accurate to like about 5 decimal places. All right. His real achievement, the most sort of amazing thing that he did, he considered to be like the greatest thing of his life, and this is maybe the pinnacle of ancient Greek mathematics, is he found the area of a parabolic segment. So all this stuff in here. Actually, hold on. I want some more advanced. Um, can I do like, okay, well, I shouldn't bother. Yeah. Let me not try to be cool. So how do you find the area of a parabolic segment? All the stuff inside this parabola. Okay, and I don't want to go into any of the details, but he did it. And in particular, what he found was that if you go over here to this point, such that the tangent line to the parabola is parallel to the segment that's being cut off, then if you connect this, you get a certain triangle. And if you then, let's experiment with some new, yeah, that's kind of pretty. Then if you fill that in, that is a certain triangle. And in fact, he claims that the area of this entire parabolic region, it's called a parabolic segment, is 4/3 times the area of this triangle. And why? Well, as you can sort of see from this, the spaces that are left over when you draw this triangle is like another parabolic segment. And so, if I sort of repeat this process all over again, then I get by drawing a tangent line, drawing this in here, drawing this in here. Okay, this picture's terrible, but then this is another triangle, and he determined with basically with geometry that the areas of these triangles form like a certain geometric sequence. And so every single step in the algorithm, he was exhausting, which is to say, using up all of the area inside the parabolic segment. And his end result was that the area was exactly 4/3 the area of this big blue triangle. Okay, this is supposed to be giving you a taste for calculus. What's calculus about? It's about finding the area. One thing it's about is finding the areas of curved regions by splitting them up into an infinite number of infinitely small things that I do know how to find the area of, and sort of continuing this process forever. And this is relevant for all kinds of shapes that you might want to study. For example, um, I bet that you probably never received in your education a quality proof for the surface area of a sphere or a proof for the volume of a sphere. These are other curved regions, and anytime you want to find the area of a surface area of a sphere or surface area of a surface area of a sphere, surface volume of a sphere, you're going to have to use, this thing that I call baby calculus, where you're splitting things up into an infinite number of infinitely small pieces. Okay, moving right along. So this is the area problem. Okay, great. Let's fast forward. Let's fast forward like, 1900 years or something like that. And let's go to this thing called the tangent line problem. The tangent line problem. What is the tangent line problem? This is due to Newton and others. I'm just gonna kind of lie, and I'm gonna say a bunch of history, which is not actually correct, but it is convenient. 1660s, basically, that we think of Newton as inventing calculus. But okay, how does Newton invent calculus? Why? What are his motivations? All right, here comes the big lie. Newton invents calculus to solve certain physics problems. Okay, what kind of physics problems are we sort of talking about? Well, let's do some very simple kind of middle school physics problems. And also, you did these in freshman physics. So consider that we're taking a trip, and suppose we're going from DC to New York City. Okay, this is a distance of approximately 240 miles, let's say, and also this trip tends to take about 4 hours if you drive, very quickly. Okay, so suppose that is exactly what happened. Suppose you traveled the 240 miles. Aha, figured it out. And it takes exactly 4 hours. Now I might ask a question, how fast were you going? Okay, well, careful people will realize that that's not maybe like a good question or something. How fast were you going? Because you could have been going at different speeds at different times. So really, the question that's being asked is, what is your average speed? And your average speed for an entire trip is just, this is sort of what we mean by average speed, the total distance that you traveled divided by the total time that the trip took. This is how fast you were going on average. And the answer is that we traveled the distance of 240 miles and it took us 4 hours. And so you divide and okay, congratulations, we were going, 60 miles per hour. Okay, great. Um, What if, okay, so let's just pretend, scenario number one. What if you really were going exactly 60 miles per hour for the entire trip? Well, we can make a chart, a graph, and this is like a kind of a distance versus time graph. So we're gonna put, distance from DC on the vertical axis, and we'll put sort of like, time on the horizontal axis, measured in hours, and this measured in miles. Okay. And all right. Well, so here's sort of the deal. If this is 4 and this is 240, then it took me exactly 4 hours to go 240 miles, but I was traveling at a constant speed the entire way. Well, if you're traveling at a constant speed the entire way, then your distance versus time graph is going to be a straight line because in every sort of hour that goes by, you cover exactly 60 miles, and so your line is it's line because the rate of change of this curve is constant. You're always going exactly 60 miles per hour. Okay, so this is maybe sort of boring, and in some ways, this graph doesn't help us so much understand this problem. Notice that when we asked you the question, how fast were you going on average, we solved it by just, thinking and using the definition of average speed. It didn't require us to make a graph. Okay, but more complicated graphs do require, more complicated scenarios, maybe the graph would be more helpful. So here's a scenario. Let's call this scenario number two. In scenario number two, now let's see if I can squeeze this in. Same basic setup. It's still time in hours on the horizontal axis, and it's still, distance from DC on the vertical axis, we are still going to complete the entire trip, which is 240 miles, and it's still going to take us 4 hours. But the way in which it happens is kind of different. We're going to end up maybe getting stuck in a lot of traffic coming out of DC, such that we only make it 60 miles in the first 2 hours. But then we really speed up and get some kind of, police escort almost type thing going on in those last 2 hours. Okay, so just to make sure everyone's clear on this, what we're really can ask now about this graph is we can also ask for the average speed on various intervals. And so I can sort of ask you, all right, what is the average? This is for the second scenario, average speed on the interval 0, 2? Well, the average speed on the interval 0, 2 is going to be the total distance traveled on the interval 0, 2. And that would be this height um, divided by, so that's 60, um, divided by 60 miles, divided by the amount of time that went by. And so that would be this one. So, and the amount of time that went by is 2 hours. Okay, so, duh, we went 30 miles per hour because, again, it took us 2 hours to go 60 miles. Okay, great. And let's do another one now. Let's switch back to, yeah. So now, second question. What is the average speed on the interval 2, 4? Well, again, this can be calculated sort of just by thinking. It's just going to be the total distance traveled during the second half of the trip, which is going to be 180 miles. But now we divide by the total amount of time that that took, which is 2. But if you want to sort of visualize this on the graph, this is kind of the 180, and this is the 2, just like this was 60 and this was 2. And so I'm beginning to sort of see what's kind of going on here. What's going on here is if I want to find the average speed, then if I'm viewing it graphically on a distance versus time graph, then I'm really taking kind of like the ratio between two things. I'm taking the ratio between the vertical change and the horizontal change. And you can even see this as being kind of like a line here. And if you see that red thing as being like a line, then this 60 divided by 2 is like the slope of this line. So the slope of this line is the change in y over the change in x, which is 60 over 2, which is the average speed on that interval. And doing it for the other one, we get kind of the same thing. We have now a dip. Oh man, we have a different line. And what is this slope? Well, it's the change in the y, which is 180 over it's the change in distance over the change in time. So again, that slope, the ratio between the side lengths of that triangle, that gives me the average speed on that other time interval. Okay, perhaps you just completely and totally learned this in middle school or freshman physics, or it's just kind of so obvious anyway that it requires no thinking. But all of this is to sort of remind you that if I have a graph, let's get serious now. If I have a graph, so here we go, doing more general now. If we have a distance versus time graph, and now I'm going to draw one sort of, generically or something, and you give me a particular time A and a particular time B, and ask me for the average speed or average velocity. In this case, we'll keep it simple because our distances are all going to be increasing. The average speed on the interval AB, average speed on the interval AB, then of course I can answer this just with thinking. The average speed on the interval AB is just going to be the total distance traveled on the interval AB. The A and B are times divided by the time, and the time is going to be just the time that elapsed, which is B minus A. Okay, and so that's the answer. But if I make a kind of picture of this on the graph, I see we can even give this function a name. We can call it f. This is kind of a comma f of a. And so this is a maybe it's better if we just do this properly or something, and we don't say well, whatever. We don't have to do this so properly, but I'll call this is position. In other words, this function f takes as input a time and outputs kind of, where you are. In this case, it's how far away you are from DC. Okay, and over here we have this point, which we can give it coordinates, b comma f of b. So that's b is the time and f of b is the position. Okay, and so what I'm realizing now is that there's this triangle which is kind of begging to be drawn, and this triangle, this right triangle, has kind of a horizontal leg of b minus a. But what is b minus a? It's the time that was elapsed. And then we have this vertical leg of this triangle, which is f of b minus f of a. And what's that? Well, it's just the total distance traveled on the interval AB because we end at position f of b and we started at position f of a. And so the change in the position is just the amount of distance that I traveled during that time interval. Okay, and so this is the formula for average speed. Duh, you could know that without drawing any pictures. But what I begin to realize is that this line has a name. Why isn't this working? Yeah, this line is called the secant line, and the secant line is this line which kind of cuts through the function at these two places. And the if you want to know, this is the big takeaway here. If you want to know the average speed on a certain time interval, it's just going to be the slope of this secant line. So I hope everyone sees that the slope of this line is, what is the slope? It's just the change in y over the change in x. But in this case, the slope is f of b minus f of a, the change in position over the change in time. Okay, great. We don't seem to be doing any calculus yet. I agree. Where does the calculus come into it? Well, this calculus comes into it when we start to ask, sort of more difficult questions. Like, so I'm gonna put this picture back up again. Yeah. And now what I want to do is instead I want to know at time A exactly um, how fast am I going? Okay, so what I want now is the instantaneous velocity um, at time A. This is a much harder question. I know how to find the average velocity over some kind of interval, but I want to know the instantaneous velocity. Okay, and the way this kind of works is one way to sort of do this is to sort of if we were live in class, I would do this kind of whole fun conversation, but maybe it won't work over video. But what does it even sort of mean to say you're going at a certain speed at a certain time? So if you ask a bunch of people, hey, what is it? How fast am I going? Right now, they'll give you a certain answer. Okay, so what's up with that answer? How can we understand that answer? What does it mean to be going a certain speed at a certain time exactly? Well, some people will just, they'll look at their speedometer and they'll say, oh, well, my car is telling me that I'm going, at this exact speed. Okay, but what does that mean? How does your car know? Where are these kind of reports coming from? If you really sort of think about it, if you freeze time at like an instant, and you ask, how fast am I going, at this instant, you can start to kind of confuse yourself because in a particular moment, of course, what is velocity? It's distance over time. But how fast am I going if you give me a time interval of length 0? Well, then no time has elapsed and no distance has been covered either because you're sort of freezing everything in an exact moment. So this is kind of like a 0 over 0 or something like that. So, all right, if you get kind of introspective and sort of philosophical about the very meaning of instantaneous velocity, you can kind of start to sort of worry, wait, what does this kind of concept even sort of, make sense? And this is the kind of thing people worried about. All right, well, what you can do, certainly, if you're not too worried about this kind of stuff, what you can do is you can look at a really, really tiny time interval. Uh, in other words, what you might think is, okay, well, I don't know exactly what the time is, what the velocity is at time A, but what if I just scoot over like a little bit to this point B, which I think of as being, very, very close to A. And now we can just repeat the conversation um, from the previous slide that and if you give me the slope of this um, of this line, this secant line, that will give me approximately how fast I'm going at time A. And then this approximation can be made better by moving this point closer and closer. And so if I move this point B, let's just call this, like B2 or something like that, to a point that's very, very, very close to A, well, then I can draw the secant line through those 2 points. This picture is so bad, it's basically unreadable. But all right. Hopefully you guys are getting this. The goal is if you move the 2 points kind of like on top of each other, then that should sort of give you the answer to the overall question. All right. Here's my attempt to sort of redraw this again. This is this is again the position versus time curve. And what I'm hopefully you guys are realizing now, if you've never heard of this before, the sort of whole thing that we're trying to do is to find the slope of this tangent line. And what is a tangent line? A tangent line is a line that touches the curve at exactly 1 point. And the reason why we care so much about the tangent line is because the tangent line is just what happens when you take the 2 points of the secant line and sort of move them on top of each other. And so what we're really doing is we're finding the instantaneous velocity. So the instantaneous velocity is just the slope of this line. And so, okay, to sort of wrap this up, we have this thing called the tangent line problem. And the tangent line problem says, I want to be able, for any function whatsoever, at any point on that function whatsoever, to be able to find the slope of the tangent line to that curve. And I care about this because if I can find the slope of the tangent line, then I can know the instantaneous velocity. Okay, so that's one of the two problems of calculus. One is the area problem, and one is the tangent line problem. But wait, we're not done. Back to the area problem. Back to the area problem. If we revisit the area problem, so this is now the problem that we were looking at earlier. Oh my God, I'm so sorry. This video is so long. Hopefully you're watching on 2 times speed. We kind of rambled for a long time, including some, detouring to parallelograms and crap like that, looking for formulas for the areas of all the sort of basic shapes. That was kind of the old area problem, and it wasn't really a problem until we got to curvy bits. And when we get to curvy bits, we had to split them up into an infinite number of infinitely small things so that we could put it back together and get something that we understood. Okay, well, the area problem kind of comes back again in the 17th century, and it turns out to be relevant again for these kinds of physics problems. So now, suppose that you were going 60 miles per hour, and suppose you traveled for 4 hours at 60 miles per hour. Well, question, how much distance would you have traveled? Well, duh. The distance that you would have traveled would be exactly 240 miles. Anyone who understands what a rate even means, that's what 60 miles per hour is. You cover 60 miles every hour and you travel for 4 hours. So this is kind of like a duh type situation. This is what they teach you, distance equals rate times time. That's all the kind of physics that you need for this. Okay. So therefore it seems almost silly to draw a picture of this, but I shall anyway. What I'm going to now draw is on the horizontal axis, time, and on the vertical axis, velocity, so speed that we're going. And here we were going 60, and we went for 4 hours. And okay, I'm being asked to multiply 60 times 4. And so, to me, multiplication means, find the area of. And so, almost against my will or something, I am seeing this rectangle forming before my eyes. And this rectangle is a rectangle whose area is 60 times 4, which gives me the total distance traveled. Okay, so that's kind of interesting. Let's go to a new problem. Let's go to a different velocity versus time graph, which is not so boring. But this one's still kind of boring. So let this be one, and let this be, two, three, four. And let's just suppose that my velocity, while not constant, is kind of, piecewise constant. So this could be 30, this could be 60, this could be 90. And so in the first hour, I'm going 30 miles per hour. But then at that exact moment that I hit the 1 hour mark, suddenly my velocity picks up. And now I go 60 miles per hour, and I managed to go 60 miles per hour for the entire middle portion of my trip. And then for the final hour, I really kind of gun it, and I go 90 miles per hour, but at a constant rate for that entire fourth hour. Okay, so what can be said about this? Let me try my new see if I'm getting any better over the course of this video. So here we have so I now ask the question. All right, great. How much distance did I travel on this entire trip if I was going at these various speeds for these various times? Well, again, the picture is barely helpful because um, I can just calculate that, dude, I went, 30 miles per hour for 1 hour. And so obviously I traveled 30 miles during that first hour. Okay. What about during the middle portion? Well, during the middle portion, I traveled for 60 miles per hour for 2 hours. And of course, that's going to give me 120 miles. But are you starting to get kind of like a feel for what's going on here? You really just have all these rectangles, man. And every time someone is asking you to find the total distance traveled, if you're going at a constant rate, well, you can just sort of think of that geometrically as oh my God. You can just think of this geometrically as the area of a certain kind of rectangle. Here, I'm going a total distance of 90 because 90 times 1. Okay, so I begin to sort of associate the total distance traveled with the area underneath these velocity versus time curves. Okay, now comes the sort of final problem, the one that's a little bit more reasonable. So this is sort of like scenario three now, where here my velocity is not constant, and nor is it piecewise constant, but instead it's, some kind of nice smooth curve like this. Okay, and here, this is maybe two, this is maybe one, this is maybe three, this is maybe four. Now the question is a much harder one. I would like to know my exact distance traveled during this time interval. And okay, here it's kind of tricky, but what we can do is motivated by the thing we just did a minute ago. We can again sort of draw rectangles. And I can draw this rectangle here. Okay, this is maybe the hardest thing I've tried to say so far in this video. What is the meaning of this red rectangle? Well, you multiplied 1 hour by a certain velocity. And when you multiply a velocity by a time, you get a distance traveled. But the area of this red rectangle is not actually the distance that we traveled during this first hour, because you can see that it's way overestimates the actual distance that was traveled, because we're assuming on for this entire hour that we were going at this very high speed, but actually we were only going at that speed at the end of the hour. Okay, so to be extremely precise, the meaning of this red rectangle, the meaning of the area of this red rectangle, is it's the amount of distance that I would have traveled if I had been going for the entire hour at the speed I was going at the end of that hour. Okay, and now we can repeat. So going over here to the second hour, again, we see that this blue rectangle overestimates the true distance traveled for this object moving according to this velocity versus time curve. this blue rectangle, its area is the distance I would have traveled if I had been going for the entire hour at the speed I was going at the end of that hour. Okay, and now just two more times. Here we go. Boom, boom. Um, and here we have that's clearly an underestimate of the true distance traveled. And here, again, we have like an underestimate. Okay, so if you add these all up, um, what you perhaps end up with is something that's, sort of, close. It's kind of prettier if we end it like that. It's a sort of an approximation to the true distance that was traveled. And it's maybe not such a bad approximation. Okay, in keeping with everything that we've just done, this works better live, but I now ask for class, how could we make this approximation better? And I think the answer is obvious. We can make this approximation better by using more rectangles. And so if you use instead of four rectangles, 8 or 16 or 32 or 64 rectangles, now suddenly the rectangles are giving a quite good approximation. And so you're sort of pretending that your velocity versus time curve, which was variable, is made up of thousands or millions or even an infinite number of these tiny, tiny little rectangles. And each one of those tiny little rectangles represents a tiny little bit of distance traveled. Okay, and so the true modern area problem is the problem that says for any curve whatsoever, try to find the area under that curve. And if you can find the area under that curve, then you can find the total distance traveled, even when that velocity curve is sort of changing all the time. Okay, these are the two big ideas of calculus. And this is what we're going to do. Over the course of this entire semester, we are going to solve the tangent line problem, and we're going to solve the area problem. We're going to solve the tangent line problem very soon. And we're going to solve the area problem in April and May. And okay, how do you solve the tangent line problem? Well, it's maybe kind of hard, or maybe it's sort of not so hard. In fact, maybe we should just, do it right now or something, why wait? Okay, so let's take a really simple curve, the simplest curve I can think of. Take the function f of x equals x squared. Okay, and suppose I want to know. So what I want is um, slope of tangent line at 3 comma 9. Okay, so you can think of this as a pure geometry problem. So 1, 2, 3. 9 is way up here. Wait, hold on. I want to do that whole thing over again. 3 comma 9. So let me make a better picture. So let's let this be 9 and this be 3. And so, okay. So, oh boy. Great. Okay, so there's my parabola looking quite terrible. Okay. And this is the point, 3 comma 9. Okay, now if you want to bring physics into this, you can think of this as time, and you can think of this as position, and then the asking for the slope of the um, uh, tangent line is like asking for the instantaneous velocity. But as we kind of discussed, instantaneous velocity is sort of impossible. What is possible is average velocity. And so I can, in order to solve this problem, I can find the average. What I want now is the average velocity over a tiny interval near 3. Tiny interval near 3. In other words, I'm going to pick a number which is only a tiny bit more than 3. Let's call it x, where I think of x as being very, very close. And now I'm going to go up to the curve, and I hit this point x comma x squared. Okay, and well, now there's like this, little rectangle here, no, triangle here, And what are the dimensions of this triangle? Well, here it's x minus 3, and here it's x squared minus 9. And the overall goal is, well, this is not even the overall goal, but one thing I can certainly do is draw the secant line to through those 2 points. And if I draw the secant line through those 2 points, it looks so bad. Can't believe it. Looks something like this. Yeah. Then this is the secant line. Then the slope of that secant line would give me the average velocity. So okay, so average velocity over. So let's just do it. So what is the average velocity on the interval 3x? Well, it's just going to be the slope of that green line, which is the change in position over the change in time. And the change in position is just how much distance was covered during that tiny, tiny time interval, which is x squared minus 9, and divided by the tiny amount of time that elapsed, and the tiny amount of time that elapsed is x minus 3. Okay, and here you might be very, very tempted, and this is, don't resist the temptation, to just factor this. This is in fact x squared minus 9 over x minus 3. Isn't this just x plus 3? Yeah, it kind of just is. And then, since this is just x plus 3, then what is this approximately? What is x plus 3 approximately when x is approximately 3? It's about 6. Okay, so believe it or not, that's the right answer. And believe it or not, we have just calculated the slope of the tangent line to the parabola at x equals 3. It's actually just that easy. It's 6. All right, and now we have to sort of sit back and ask ourselves, man, what even happened? So sort of like sort of stuff is going on here. Here I am taking kind of an approximation, and I'm saying that I want this to be the final answer, but I'm being, a little bit tricky here because on the one hand, I'm pretending that x is not 3 because of course if x is 3 exactly, then this division is impossible. But then over here, I'm just kind of pretending that x is 3. And so there's some sort of tricky little game going on here with infinity. And we have to get really good at that game so we don't kind of mess it up. All right, and so we have some notation for this. We say that the limit as x approaches 3 of x squared minus 9 over x minus 3 is 6. And when we use this phrase, the limit as x approaches 3, what we're really saying is take this ratio, which is the slope of this secant line, and sort of ask and answer the question, what is this ratio when x is very, very close to 3? And when x is very, very close to 3, we say that this is very, very close to 6. Okay, this is going to require like more care or something. And so we better get good at limits. All right, so the last thing we're going to do in this video is I'm going to sort of teach you some stuff about limits. Intro to limits. This is going to take 5 minutes. And maybe we'll do like one problem together or something. Okay, I'm going to give you 4 examples and of limits, and sort of here they are. Can I squeeze these all in? Sure. So let's look at something like this. Yeah. And maybe we have some functions coming in like that. And then, okay. And this is A. And let's call this L. And we'll call this M. Okay, so here is what I'm teaching you now. I'm not explaining it sort of deeply. I'm just giving you the basic gist. What is the limit as x approaches a from the right of this function? All I mean by this is, what is this function doing? What value does this function have approximately when x is really, really close to a, but a little bit more than a? Well, you just look over here. When x is a little bit more than a, this function is pretty much just m. So there's your answer. Okay, what's the limit as x approaches a minus of f of x? Well, this just asks if you give me a number which is a tiny bit less than a, what is this function approximately? Answer, L. Okay, but then if I ask what is the limit as x approaches a of this function, what I'm really asking for is near x equals a, what single number can I report as being the value of this function approximately? Let me say that again. Near a, what y value does this function have, more or less? Well, I cannot answer this question. This limit does not exist because there is no single number which describes what this function is doing near a. To the right of a, it's approximately m. To the left of a, it's approximately l. But at a, this limit does not exist. Okay, let's do another one. This is another function. Here is a, and okay, now I can ask what is the limit as x approaches a from the right. Now, notice when I ask for the limit as x approaches a, I'm not ever asking about what's actually going on at a. Just what is this function approximately when x is near a. So if x is a little bit to the right of a, well, this function is pretty much just L. And what about as x approaches a from the left? What can I say about this function? Well, if you give me a number which is a little bit less than a, this function is still pretty much just L. And so here we say that the limit as x approaches a of this function is L, because whether x is a little bit more than a or a little bit less than a, the value of this function is very close to L. Okay, there's two more pictures that sort of expand our kind of vocabulary for limits. We also sometimes want to talk about end behavior, and so we have kind of like this sort of thing, and we have a little some function that maybe looks kind of like this. And what would we I would like to say about this function is that the limit as x approaches infinity of this function. Well, now I'm asking kind of a little bit of a different question, which is when x is very, very big, what is the value of this function approximately? And the answer is it's k. And the sort of final thing that I would like to talk about is maybe there's a kind of like a volcano situation happening here for near a. And so we also say that the limit as x approaches a of this function is infinity because this function is just becoming infinitely big. Okay, what I would now do, this was all supposed to take 90 minutes, but I think it took way longer. It's making me really sad is pass out a worksheet. And this is the worksheet that I passed out on the final day of school, the final day of first semester. In my pre-calc class, I did at least. I think Dr. Castro passed it out also. If he didn't pass it out, it's available anyway from Canvas. And I want you, in addition to watching this entire video, I want you to do this worksheet. And so here we go. The very first problem of this worksheet is what is the limit as x approaches 1 of x cubed minus 1 over x minus 1? Okay, and it's really sad to be doing this on video. In fact, it's giving me bad memories of trying to teach on during the pandemic. It's basically terrible. So students, please come back as soon as you possibly can. But what happens now is I pass out this worksheet, I put you all into groups, and everyone just kind of fights, argues, haggles, and many very, very interesting things happen. And one thing that happens, it really is kind of the luck of who happens to be sitting next to you, is people just are fall apart and start making, terrible and ridiculous claims and fall into traps and stuff like that. Sometimes there's some really good dialogue and conversation, so none of that's happening right now, of course. What some people do is they just think it out, man. Okay, Mr. Rose told me that a limit describes the behavior of this function when x is really, really close to 1. Well, what is the behavior of this function when x is really, really close to 1? Okay, well, let's look at it one step at a time. This numerator, if you plug in a number that's really close to 1 and you cube it, well, that's also really, really close to 1. and minus 1, this is just going to be something that's very, very tiny. And down here, if you plug in a number that's very, very close to 1, this is also going to be tiny. And so you're kind of like dividing a really, really tiny thing by another really, really tiny thing. And this is maybe 1. Or some people will just write 0 over 0, or some people will write, does not exist because this you hear you're dividing by 0. Okay, all sorts of crazy things can happen if you're not thinking clearly, and this is an indication why this topic is kind of very tricky. And by the way, we have now entered this first unit of the semester, and the first unit of the semester is limits. And what are limits? It's these things we're doing right now. Why are we doing it now? We're doing it now because limits are going to sort of train us to be really, really good at dealing with manipulating infinitely large and infinitely small quantities. And so we're actually going to put the tangent line problem on hold for like 3 weeks, and we're going to return to it after we become kind of like experts at infinity. And what some people see immediately, whether because of deep thoughts or whether just because they've just been trained or something to do math, and that is that we can factor. So okay, and if you do that, if that was your first thought, then great, that's a great thought. This is the difference of cubes. You all know the difference of cubes formula. It's this, and so since you can factor, now the next question is, can we cancel? Yes, we can cancel because remember, when I asked you what is the limit as x approaches 1, I'm not asking what the function is doing at 1. Clearly, at 1, this function is undefined, but near 1 is the question that's being discussed. And so, since x is never going to be 1 exactly, then this is perfectly legitimate to cancel these two. And so this is kind of like revealed to be this problem here. And what happens near x equals 1 to this quadratic, it turns into 1 plus 1 plus 1. And so the answer to this problem is 3. Okay, good. um, yeah, so first of all, that shows that the tiny over tiny equals 1 people were just wrong, because tiny over tiny does not always equal 1. In this case, it equals 3. And that's because this is sort of the reason why. All right, you have this worksheet. I want you to do the rest of this worksheet, and I want you to have it done by class on Tuesday. So that's watching this entire video. Which is going to be like 90 minutes long or something on hopefully like 1.5 speed, if not faster. And then I did my best with the materials I had here um, at my disposal in my home. I'm sorry about the bad handwriting. And if you're in my class, then I will see you as soon as we get back to school and we'll do some calculus. And if you're not in my class, then I'm sad, but you will have Dr. Castro and he will do the same thing as I do all semester because that's because we're doing this together. And so, all right, here's the intro video. Hopefully, you got a big taste of calculus. You got a review of all of your area formulas from middle school geometry. You got some appreciation for how difficult it is to find the area of a circle and to find the the volume of a cylinder and the volume of a sphere and all these kinds of tricky problems that you will be able to solve by the end of this course, easily. And you got some appreciation for the history of calculus, although it's fake history. But basically, there were certain physics problems that I wanted to be able to solve, like to find the instantaneous velocity, and for that I can find the slope of the tangent line to the curve, and back to the area problem. And now the sort of usefulness of this kind of thing with limits. Should I do one more problem? I'm feeling guilty like I should do one more together with you. Let's do one more. Let's do problem number 2. Problem number 2 says, what's the limit as x approaches 0 of 5 sine 2x over x? And if you think about this, you might also be tempted to say that this denominator is approximately 0, because that would be true. And this numerator is also approximately zero because if you take the sign of something that's very, very tiny, you get something that's very, very tiny. And something very, very tiny times 5 is also something very, very tiny. And so we again have this kind of tiny over tiny situation. And yet, the answer is not so simple. What can we do here? There are many things we can do here. One thing that some people might think to do is to do a trig identity. So the more you know, the more options you have. And I know that sine 2x is 2 sine x cosine x all over x. Well, does that help at all? I think it kind of does because on the one hand, cosine, oh my God. On the one hand, um, whoa, sorry, zoning out. On the one hand, cosine x near zero is going to go to 1. And then on the other hand, you are supposed to have some deep memory from pre-calc C about sine x over x. This is something that came up in like October. And when it came up in October, we drew this kind of picture where we said that the arc, the input to the sine function is always an arc length on the unit circle, and this is always sine x, and so sine x is always going to be a little bit less than x. But on the other hand, when the arc is very, very, very tiny, the sine x is kind of like almost the same thing. Okay, worst picture ever, but what this means is that sine x is approximately equal to x when x is very, very small. And therefore, all this stuff in the orange circle, this is an example in which tiny over tiny is 1. But if that orange thing is going to 1 and the thing in blue is also going to 1, then the overall answer to this problem is 10. So in general, tiny over tiny is not 1. Uh, in this case, tiny over tiny is 10. Okay, so hopefully that gives you some sort of basic gist of how to do limits. You're on your own to figure out how to do the rest of the worksheet, and I will see you when I see you back at school. All right.